You open ChatGPT without typing a formal setup prompt. Instead, you rely on voice input, quick, natural, almost like thinking out loud. And the first thing that lands on the screen is a simple question. What do you know about the Tic Tac Toe game? Nothing complex, nothing structured yet. Just a raw entry point into the system, like knocking on a door before you decide what room you want to build inside. At this stage, the intention isn't just to ask about a game. The intention is to anchor the model into a single domain. Tic Tac Toe becomes the training ground, not in a literal machine learning sense, but as a controlled context where everything that follows stays focused, consistent, and predictable. One topic, one mental model, one evolving system. From here, the real direction starts to form. You're building a process-driven tutorial. The goal is to demonstrate in an uncut and transparent way how a product requirements document, PRD, can be created step by step using ChatGPT, not as theory, but as live construction, where each response from the model becomes part of a structured build sequence. Instead of jumping directly into code, the flow is intentionally layered. First, understanding the game, then defining structure, then breaking down requirements, then slowly transitioning into implementation. This mirrors how real engineering systems are designed. Clarity before creation, design before development, logic before output. What you're effectively doing is turning a simple question into a controlled learning pipeline. Tic-tac-toe is just the starting sandbox. The real product is the method itself, how someone can take a basic idea, shape it into a PRD, and then progressively use ChatGPT to generate working code without skipping the foundational thinking. What you just observed is a textbook case of an algorithm crossing its computational feasibility boundary. And it's one of those moments where a working game quietly turns into a systems design lesson. Let's unpack it properly in a way that fits your uncut testing narrative. At the beginning of your testing, everything behaves exactly as expected. In 3x3 mode, both player versus player and player versus computer run smoothly. Moves are instant, the AI responds quickly, and the game feels stable and predictable. This is because the underlying AI logic, most likely a minimax based decision system or similar recursive evaluation strategy, is operating in a small, fully enumerable search space. In a 3 and 3 tic tac toe board, the total number of possible game states is relatively limited. Even though the branching factor exists, the depth of the game tree is shallow enough that the AI can evaluate all possible moves, all possible opponent responses, all possible future outcomes, and still return a decision almost instantly. So, in this environment, brute force reasoning is not just acceptable, it is optimal. Then you move to 4x4, and this is where the first hidden stress begins to appear. The system still works, but the computational cost quietly increases. The number of possible moves per turn increases, and the depth of the decision tree expands significantly. The AI is now evaluating a much larger search space, but it still manages to complete its reasoning within a tolerable time frame. What you are seeing here is the AI transitioning from open quote, instant full search, heavy but manageable full search, close quote. At this stage, it still behaves correctly, but the architecture is already under pressure. Now comes the critical shift, 5x5 mode. This is where everything changes. When you play a move in a 5x5 tic-tac-toe board, the AI attempts to apply the same logic it used in 3x3. Simulate every possible AI move, simulate every possible player counter move, recursively continue this pattern, evaluate all outcomes to choose the optimal move. But here's the core problem. The game tree does not grow linearly. It grows exponentially. What brute force thinking actually means here, the AI is not thinking like a human. It is not estimating, it is not guessing, it is trying to be mathematically perfect. So it performs what is essentially, open quote, a full recursive exploration of all possible future game states, close quote. This is called brute force minimax search. And in a 5x5 grid, this becomes extremely expensive because there are more empty cells per turn, there are more possible move combinations, the depth of possible games increases, win condition evaluation becomes more complex. The branching factor multiplies at every recursive level. So instead of exploring a small tree, the AI is now trying to explore a massive combinatorial explosion of possibilities. Why it looks like an infinite thinking loop. What you experienced as infinite thinking is not truly infinite. It is a performance collapse caused by recursion overload. Here's what is happening internally. 1, you make a move. 2, AI starts evaluating all possible responses. For each response, it evaluates your possible replies. 4, this continues recursively. 5, the number of branches grows exponentially at each depth. At 5x5, the number of possible sequences becomes so large that the recursion depth increases dramatically. CPU time per move spikes. The system stops returning control quickly. So from your perspective, the AI just never moves. But internally, it is stuck inside an enormous decision tree, trying to complete a computation that is no longer realistically bounded. The key design flaw revealed by your testing. This is the most important insight. The AI logic was designed under a 3x3 assumption model. That means, open quote, I can fully solve the game tree every time before making a move. Close quote, Todd. That assumption is valid only when the state space is small. But when you scale to 5x5, the state space explodes, full search becomes impractical, the algorithm loses its ability to terminate quickly. So the system is not broken randomly. It is failing because it is being asked to do something it was never designed to scale for. Why 3x3 and 4x4 still worked. 3x3 full minimax is trivial, 4x4 still solvable but heavier, 5x5 exponential blowup threshold crossed. So what you are observing is a scaling cliff, not a gradual degradation. Everything works perfectly until a threshold is crossed. Then performance collapses suddenly. The deeper engineering truth. This is not just a bug in tic-tac-toe. This is a universal AI principle. Open quote, perfect decision-making algorithms do not scale infinitely. Close quote. At small sizes, brute force intelligence looks powerful. At larger sizes, it becomes computationally impossible. So systems must shift from perfect search, approximate reasoning, full evaluation, depth-limited evaluation, brute force, heuristic evaluation. Why this matters in your project workflow. What you have discovered is extremely valuable. You are no longer just building a game. You are stress testing an AI decision system across multiple complexity layers. And you have proven UI scales, game logic scales, AI strategy does not scale. This is exactly the kind of failure real engineers look for because it tells you where the architecture must evolve. Final insight, what this really means. The AI didn't freeze because it was confused. It froze because it was being too correct for its own good. It tried to solve the entire future of the game perfectly, instead of making a fast, good enough decision. And in real-time systems, that difference is everything. If you continue this series, the next natural step is not fixing the game, it is redesigning the AI from, open quote, perfect solver to bounded intelligent decision maker, close quote. That is where your system stops being a demo and starts becoming an actual scalable game engine. Now we've reached the most important and honestly most realistic phase of any real-world development cycle: partial system breakage due to overcorrection during debugging. What you are experiencing right now is not just another bug. It is a cascade failure caused by iterative patching without full state validation. Let's reconstruct exactly what happened in your system so you can narrate it clearly in your uncut video. What just happened in your project? After identifying the AI performance issue in 5x5 mode, you began making corrective instructions to DeepSeek. The intention was correct: reduce brute force search, prevent infinite thinking, stabilize AI decision time, make higher grid sizes playable. But something important happened during repeated regeneration cycles. Open quote, each fix optimized one part of the system while unintentionally breaking another dependency. Close quote. Now the system is in a partially inconsistent state. The real technical reason everything is breaking: your game now has three tightly connected subsystems. 1. Game engine, board's rules, 3x3, 4x4, 5x5, grid logic, win condition logic, move validation. 2. AI decision engine, move evaluation logic, minimax heuristic switching, depth control logic. 3. Event loop turn controller, detects player move, triggers AI response, updates UI state. Where the break actually occurred: during your debugging instructions, AI logic was modified to fix 5.5 freeze, depth limits, heuristics were introduced. Regenerated full file code replaced previous stable structure. But here's the critical failure. Open quote, the AI fix unintentionally broke the turn execution pipeline. Close quote. So now what happens is, player makes a move, game tries to trigger AI logic runs but never returns properly, turn cycle never completes, UI appears frozen. Why both 3x3 and 5x5 are now broken. This is very important for your script narrative. Earlier you had 3x3 stable, 5.5 AI freeze only. Now after fixes, nanner 3.3 broken, 5x5 broken. This means, open quote, the fix was applied globally without preserving base case logic, close quote, so the system lost its safe mode. The core engineering mistake, what you should say clearly, what happened is a classic mistake in iterative AI-assisted development. Open quote, we optimized the edge case 5x5 but accidentally corrupted the baseline logic 3x3. Close quote. This usually happens when full file is regenerated repeatedly, no modular separation exists. AI treats everything as one monolithic script, fixes overwrite stable functions instead of patching them. What the system is doing now internally. Right now, the game is likely in one of these states. Case A. AI function never returns. Recursion or loop still exists. No timeout control. Turn never resolves. Case B. Event handler broken. Click works, but AI trigger function is disconnected. Case C. State mismatch. Board updates, but game state never advances. Why this is happening conceptually. You created a system with open quote, dynamic grid sizing plus recursive AI plus single file architecture, close quote. That combination has one weakness. Single file regeneration destroys internal consistency because every fix replaces previous stable logic working event flow, hidden dependencies. So instead of patching, you are effectively, open quote, rebuilding a new version every time with unknown regressions, close quote. How to describe your current testing phase, script style. You can narrate it like this, open quote. At this stage, I noticed something unexpected. After attempting to fix the AI freeze in 5x5 mode, the system started breaking at a deeper level. Even 3x3 mode, which was previously stable, stopped responding. This indicated that the issue was no longer limited to AI complexity. It had now affected the core game loop itself. Close quote. Open quote. This is a critical moment in debugging because it shows that iterative fixes can introduce system-wide instability if dependencies are not preserved. Close quote. What you are really doing now, you are no longer just building a tic tac toe game. You are now, open quote, stress testing a full AI-driven game architecture under iterative mutation cycles, close quote. Next step, what DeepSeek should now receive. At this point, your instruction must shift from fix AI to restore baseline 3x3 stability first, then reintroduce AI scaling carefully, ensure turn system is isolated from AI logic, prevent global regeneration override issues, add safe fallback move if AI fails. Final insight, important for your narrative. This phase is where most beginners fail, but experts recognize something crucial. Open quote, debugging is not fixing code. It is preserving system integrity while modifying behavior, close quote. And right now, your system is showing you exactly that principle in real time. At this stage, something important happens. The system finally stabilizes. After multiple cycles of testing, debugging, regeneration, and correction, DeepSeek successfully resolves all previously identified issues. The 3x3 mode becomes fully responsive again. The 4x4 and 5x5 scaling no longer causes freezes, and the AI behavior is now controlled with proper bounded logic instead of uncontrolled brute force recursion. The turn system is stable, the event flow is consistent, and the game loop finally behaves like a complete, predictable system. Now the project moves from debugging phase into what actually feels like a finished product. I review the output and respond with acknowledgement. Wow, I love it. At this point, the relationship with the system shifts from correction-based interaction to enhancement-based collaboration. Instead of fixing errors, the focus moves toward improving experience and expanding features. So I ask for further improvements. I request 5 suggestions on how to make the game better. DeepSeek responds with structured enhancement ideas, things like improving AI behavior diversity, adding animations, introducing scoring systems, enhancing UI feedback, and expanding gameplay depth. I evaluate the suggestions and don't accept everything blindly. I selectively choose suggestion 2, suggestion 3, suggestion 4, suggestion 5, and reject or postpone the first one based on design priority. Then I instruct DeepSeek to implement those selected features into the existing single-file system. At this point, the system evolves again. DeepSeek integrates the new features directly into the game, improved visual feedback during moves, enhanced AI decision variation, better UI responsiveness, additional gameplay mechanics that increase engagement and depth. The game is no longer just functional, it is becoming structured, feature-rich, and more immersive. But during final testing, another subtle issue appears. When a game ends in a draw, the system does not properly reflect that outcome in the game state logic. There is no clear reward or penalty update, and the outcome feels neutral in a way that breaks the intended feedback loop. This reveals a missing rule in the game design. Open quote, the system handles win and loss conditions properly, but draw conditions are not integrated into the reward or scoring architecture. Close quote, dot. So a final refinement is introduced. Now the draw condition is enhanced with additional mechanics. Draw detection triggers a defined game state. Respect counter or score system updates accordingly. Special event labels like shadow death or last move winner are applied based on final move context. The system now ensures every match ends with meaningful feedback, not just a neutral state. This transforms the game from a simple logic-based tic-tac-toe into a fully state-aware competitive system, where every outcome, win, loss, or draw, has structured meaning inside the game loop. And at this point, the full build is complete. What started as a basic idea evolved through discussion, PRD design, code generation, AI debugging, iterative repair, feature expansion, edge case refinement. Until finally it became a complete, polished, multi-mode Tic Tac Toe system built entirely through AI-assisted development. At this point, the game is fully complete and fully functional. What started as a simple idea, tic tac toe, has now been transformed into a complete interactive system with multiple modes, dynamic difficulty scaling, AI-powered gameplay, structured decision logic, and a fully refined user experience. Every phase of development has been tested in real time, from initial design discussions to PRD creation to code generation to debugging to performance optimization, and finally to feature enhancement and edge case handling. The final result is not just a game, it is a complete demonstration of how modern AI tools can be used to design, build, test, and refine software step by step. Player versus player mode works smoothly. Player versus AI mode is stable across different grid sizes, and even complex scenarios like draws, wins, and edge cases are now properly handled with meaningful game state feedback. Now you can experience it yourself. You can play the game using the link provided in the description below, where the full HTML file is available. Simply open it in your browser and start playing instantly. No installation, no setup, just direct execution. If you want to explore the development process further, ask questions, or collaborate on similar AI-driven projects, you can reach out through WhatsApp or check the contact details mentioned in the description. If you enjoyed this breakdown and the build process, make sure to like this video, share it with others who are interested in AI development and game creation, and subscribe for more deep, practical, real-world AI engineering walkthroughs like this. This is just the beginning. More systems, more experiments, and more AI-built projects are coming next.